Okay, so we're going to talk about limits again, but now we're going to do them analytically. So we're going to be a little more specific here and a little more precise. So the first thing we're going to do is we're going to talk about the basic property of a limit. So we're going to rewrite it here and really be clear about what we say. So we're going to talk about this limit. We're going to use LIM again to be short form of it. And the limit is always of a function, so it'll be f of x. And it's going to be, our notation is going to be for x going to, and we'll be specific here to some value c, and that limit will be, usually when we do it analytically, will be f of c. And that first step is called direct substitution. This is always our first step, apart from just looking at the limit, to see what we need to do with that limit and what we need to, how we analyze it. So an example that would be pretty clear, like if we took limit of x squared as x approaches, I don't know, 2. Now, often we'll write that here, and if you do it neatly, we're going to be fine with writing the limit this way, but we do have to be cautious when we do that. This limit is like a function in a lot of ways. It has an argument. So if you're going to write limits out, a good practice would be to use brackets, especially when the limit is a little more complicated than just x squared. For example, x squared plus 1 or something like that. So we have to be very, very cautious about those kinds of limits. So in this case, when we do that, we're going to do this as if f of x was x squared. So here our understanding is f of x equals to x squared. And so we actually do f of x. In other words, we substitute 2 for the value of x. In our function 2, we square it and we get 4, just as if we were doing f of 2. So that's an analytic limit. It doesn't have any issues. It's perfectly well defined and we don't have any problems there. And as I noted, if we do another example, limit as x approaches, let's say 1 of x cubed minus 1, this is where those brackets are going to come into play. If you're not all that neat, it's not sure, for example, do I mean to say that I'm going to take the limit as x goes to 1 of x cubed minus 1? Or do I mean that I'm going to take the limit as x goes to 1 of x cubed minus 1? Which one do I mean? If I'm not sure, I can make a mistake. So in general, when we're doing these limits and we're worrying about them and we get into this notation that sometimes will be a little bit problematic, we want to be clear here and we want to go ahead and put brackets when we need them. And I'm going to do that usually as a matter of, practice. Here I'm going to put 1 for the value of x, so I replace the value 1 here, the c value here, minus 1, 1 cubed, 1, the limit is 0. So in this case, the limit is 0. Okay, so that's the basic substitution, direct substitution to do a limit directly. And also, let's go ahead and do, that doesn't always work out. So let's just do a random example here. And this is an easy and simple one. Let's say x goes to 0 of 1 over x. Once again, I'm going to use brackets here to be sure. And this is still going to be substitution 1 over 0. Remember, that's division by 0, which is undefined. So even with direct substitution, we'll put that kind of in a gritty way, we kind of get that idea that the limit has a problem. Now, this is not entirely true because it's possible that this limit will be doing more than that. So undefined is going to be not exactly the word we're going to use for a limit, because limit, as we saw before, was kind of that process, right? It's this process as x goes to. So it's not the same process as actually doing f of 0. So these two aren't exactly the same thing. So one of the things we're not going to do is we're not going to use the word undefined. But we still can't write a number for this. So what we're going to have to do here is when we do a limit where it's equal to something like 1 over 0, we're not good enough to say undefined. We need to do more. So we have another step. So this limit will actually result in another step. And that step may give us a value where we can say the limit is equal to some value, A, or it may result in a limit that simply does not exist. Or we may say that the limit does something really interesting and it goes and gets bigger and bigger and bigger. And we talked about that the first time with limits, that it might go to positive infinity. So these kinds of limits are very special. We call them limits at infinity, and they're going to be very interesting. So we'll get back to that later on. Now there's some properties of limits that we can certainly talk about. These are very well defined. When I talk about properties and limits and these sorts of things, I'm going to keep the numbering that's the same as our book. So this is actually theorem 1.1, and this has just the basic limits. And the first part of that is going to be the limit as x approaches c of the some value b. And so we're going to have to be kind of more specific when we do that. So we say x is an element of real numbers, c is an element of real numbers, and b is a specific value. C is an element of real numbers. So c is actually in this case a positive. In fact, we can go beyond that. These are real numbers and it's a specific real number. So in this case, the f of x is constant. So when we take the limit of this, it's actually going to equal to b. So that's our first thing that we're going to do. And if you actually looked at this graphically to give an idea, f of x here is actually the horizontal line y equals b. That's what f of x equals b gives us anyways. So if we're talking about the limit as we move right or left of any value c along this line, c is an element of real numbers, this is x, this is y, we can see visually that this is always going to be the same value. The y value, which was what we're describing with the limit, is always going to be the same. It's going to be b. So that one's not really too wild for us. The second part of this theorem is going to be really kind of the straight line kind of thing. So the limit as x goes to c of x. So that's just the x value, and that is simply going to be c, and that really is just f of c is c. F of x, I should say, is c. And we can see that one as well, because once again, if we were to graph this and get an idea of what's going on with this kind of line, this is just the line y is equal to x. If we take any c along this line, the value here is always going to be f of c. And this is actually the function y is equal to f of x of x. So the y and the x are always the same value on this function. X is equal to y if you want. So if I go to c, then the value is going to be c. So that part is also easily seen graphically. Let's see now. And the next one is going to be if we do the limit, and this is going to apply to all our polynomials, is what if we do the limit of a polynomial? So that's going to be x to the n, so x to the 1, which we've got, x squared, x cubed, And all of these are going to be similar. They're going to be simply the value of the function evaluated at that value n. By the way, in this case, the n is an element of the integers and the positive integers at that. So one of the ways we will note that is use the set of positive integers, which we use z plus. So that's a way of saying, or just saying it's a positive integer. So that allows us to evaluate some limits. So I can do a real quick example. The limit as x approaches to 2 of x squared minus 2x or something like that. Now all I have to do is a polynomial, so this is going to apply to any polynomial, right? It's going to be pretty clear. It's just a group of polynomials. So this is going to be really 2 squared minus 2. So that's 2 squared is 4 minus 2 times 2 is 4 is 0. So this happens to give me 0 in that case. And that kind of suggests some properties of limits here, which will go on. We'll call this theorem 1.2. And the properties of limits. Okay, you can see that in your book very easily. So there's basic ones. First of all, if you take, let's see, B, C are elements of real numbers, N is an integer, we said, and F and G are functions. So basically the first one is going to be the limit as x goes to C of B times f of x. So it's just a constant value times f of x, and that one is going to be simply the b coming out. So, and on top of this limit, we'll have to add, let's say we have the limit as x goes to C of f of x, and we'll call that limit a specific value, L. So this is just going to be b times L. So basically, if you say 2 times f of x, you get twice the limit, that sort of thing. That's called the scalar property. Some are different, so if we take the limit as x goes to C of f of x plus b of x, kind of saw that when we did the x squared minus the 2x on the top. That's actually two functions if you want. So it could have been the limit of x squared and then minus 2x. So we have all of those things set together. So this is going to be actually the limit as x goes to C of f of x, and then plus the limit as x goes to C of, sorry, that's g of x, not b of x. Go back here and fix that. That's g of x. So in other words, we kind of did that before on the top. An example, that was the limit as x goes to C of x squared minus 2x. What we could have done with that one is simply split it apart. X goes to C of x squared, and then minus the limit of x goes to C of 2x, which either case would still be 0. So we can take it apart, but we already are doing a polynomial. But this might be two functions that aren't polynomials. So, so we'll add to this over here the limit as x goes to C of g of x. We'll say that is some value k. So if we do the limit of a complicated function, so if we do the limit as x goes to C of f of x times g of x, a product, well, that is simply going to be the limit of the two products. So it's going to be the limit as x goes to C of f of x times the limit x goes to C of g of x, and ultimately this limit is going to be L, and that one is k, so it's going to be L times k. So we got that. Property number 4, quotient would be the same thing. So if they're dividing, we're going to get the same thing. The limit as x goes to c of f of x over g of x, this one is going to be very helpful for us. So if we want to split the functions apart, we would just say take the limit of the top and divide it by the limit of the bottom. And lastly, power rule, this one could be very helpful for us if we take the limit as x goes to c of f of x itself to a power, let's say n this way, then we simply can take this and call it the limit as x goes to c of f of x. And that power can go on the full outside, and this limit inside is L, so this simply would be L to the power n. So those 5 properties are relatively easy to prove, and there's some in your Appendix A if you want to go through that and check that out. Okay, so this kind of helps you out, the limit of a polynomial, the limit of a rational function. So we can do an example of this here. And most times we really don't have to use the properties. So the limit of x going to 1 of x squared minus 1. Oh man, sorry. Ooh, even worse. Try to get my, there we go. X plus 1. So we could do this in 2 ways. We could take the limit on the top and then the limit on the bottom, but most times we're simply just going to do it and, plug it in everywhere. So we'll just do 1 on the top. There's my limit on the top, and then 1 on the bottom, or just do both at the same time. So 1 squared minus 1 is 0 in the numerator, 2 in the denominator, so we get 0 ultimately, which is a nice number. We don't have any division by 0, any issues with that one. The next step would be, of course, is composition. So that is going to be an issue. So let's be reminded of what we're talking about here. If I've got a function f of x and then a function g of x, but now I want to take a function where I do f of x and instead I put g of x as the argument for f of x. What am I going to do with that? And another way of writing that, of course, is f composite g of x with a little 0 in the middle. Be careful about that notation. So what do I do with that as a limit? So I can get that as a limit. So this is actually theorem 1.5. X goes to c, and we're just going to write that in the simplest notation possible. F of g of x. What do we do with that? And this is simply, well, we're going to take the limit of the inner part. Okay, that actually is going to be, therefore, f of, and now we're going to take the limit as x goes to c of g of x. And then whatever that limit is, let's say we say that the limit of g of x is equal to, before we use the letter k for that, so we'll be consistent. So that's simply going to be f of k as my limit. So that'll be a way of doing that. So that kind of means, in a nutshell, I could do some problem like this. F of x is equal to, let's say, the square root of x squared minus 1. So if I did the limit as x goes to 3 of that, so here I would have x squared minus 1 as my function. So I can do it in 2 ways. I can simply direct it, do it, which is probably more straightforward when we can. So I can go ahead and put that directly in the composite function, which would be 9 squared minus 1, which would be the square root of 8, which would be 4 and 2, so 2 root 2. So I can do it directly like that. Or what I could do is take the square root part out and do inside the limit as x goes to 3 of the simple part here, and that way I want to extend the square root over here. The inner part would be simply x squared minus 1, which would be again 3 squared minus 1, and then I take the square root of that, and I end up with 2 root 2 again. So that's a very interesting thing that you can do from Theorem 1.5. Further, we could do some pretty exciting things with trig. So we'll do our trig ones. That would be Theorem 1.6, where we can do trig limits. So as a list, you can see a list in Theorem 1.6 that I'll list real quick. So the limit as x goes to c of sine of x equals sine of c. So again, it's kind of the direct substitution. Notice I'm very careful. I have an argument here for sine, and sine itself is an argument to the limit. So careful you don't lose things. Your textbook tends to write things as follows. X goes to c of cosine x equals cosine c. Now that's all fine and dandy if you have a formatting processor, but if you're writing it like this, you can see, especially with my writing, which is a little sloppy, you're going to lose stuff if you do this. So it's highly suggestive to go ahead and put your brackets in so you don't lose anything while you're doing that. I always like to put my arguments of cosine and sine inside. So this is going to go for all 6 types of trig values. So limit x goes to c of tangent x. It's going to be tan c. Limit as x goes to c of secant x, secant c. As long as they're defined, we're good. And then the 2 last ones, cotangent, limit of x goes to c of tan c. Oh, I did that one. Cotan c x equals cotan of c, and the final one is cosecant. So limit as x goes to c of cosecant x is cosecant c. So all 6 are there. We've got the limits of trigonomic functions. So we can do some pretty complicated examples as we go through and working on that. One of the strengths now is we've got all those basic theorems, so we're going to do some slightly different problems. Let's do a limit like this, and occasionally we need to do this, so we're going to do a limit x goes to I don't know, let's say x goes to 1, and we'll do something like x squared minus 1 over x minus 1. This is a great example because it's going to show us a lot of things. So one of the first things we do with the limit is look at that. That's a rational function. It's going to be a little more complicated. We can see it as a function, right away. If we were graphing this function, we would make a note of that division at 0 right there, that here as a function f of x, x cannot equal to 1. So that 1, tragically, is an open value. So if I was doing an analysis of my function right away at the value 1, I would know that the function itself is undefined. But I'm not entirely sure what the behavior of my whole rational expression would be. Is it going to be one of these functions that looks something like that? I don't know. That's a big question. So part of that analysis now that we can do is to actually look at the limit, and the limit's going to tell me what happens as x approaches 1. So that's an important feature. And if I do that, if I actually play with that, let's do direct substitution, which is how we always start. And if we start with direct substitution, I would take 1 squared minus 1, 1 minus 1, and I do that and I get 0 over 0. Now that is a very unusual form, and it's such an unusual form, we're going to name it. This is called the indeterminate form. This is an indeterminate value. Is it 0? Is it division by 0? We don't know. It's just another way of saying it's actually another way of saying I don't know. I mean, literally, that's what we're saying here. But that's not good enough for us in calculus. What in calculus we want to do is we get an indeterminate form, we have to do something else. Now, what we're going to do with this form is we're going to actually do a little factoring. So I'm going to start with my expression here. I had the limit as x goes to 1. I had x squared minus 1 over x minus 1. We're going to go ahead and factor the top, so we keep the limit. We haven't changed anything. And I get x plus 1, x minus 1, and x minus 1. So notice when I factor the numerator and look at the denominator, I can see that I have a repeated factor. In fact, this factor here over that, x minus 1 over x minus 1 is essentially the same as writing 1. So we're cool. We can eliminate those, and we can totally eliminate those because we're in the limit. So those can be eliminated. We're not talking about a function here. We're not changing anything. We're just re-expressing that in the limit. So that means that we can write the limit now of simply x plus 1 as x goes to 1. And if we look at that, what we essentially are doing is we get x plus 1, that's 1 plus 1 is 2. So this limit wasn't 0, it wasn't division by 0, it's actually equal to 2, meaning that this diagram up here doesn't make a lot of sense. So let's go back down to it and see exactly what was going on. So I'm going to regraph this and put this down. I've got 1. I know 1 is undefined, but now a little more about that. It's undefined literally at that value y equals 2. So that value that we just got for the limit, the function actually is approaching the value. In fact, if I look at it here, this function literally is x plus 1, except when x is equal to 1. At that point, the function is still undefined, but the rest of the function behaves like x plus 1, which is essentially a straight line. So this is literally the straight line y is equal to x plus 1 with a hole punched out of it. X cannot equal to 1. That's all this function is, and that's what our limit helped us express, is notice as we approach this value here, as we approach the value on the left, we approach it on the right, it is approaching the value 1 comma 1, but not quite getting there. So the point 1 comma 2 here, I should say, is a point that's not actually on this graph. That's a pretty cool way of doing it. And that means we can do some pretty cool analysis when we're doing that. Another analysis that we can do would be rationalizing. So we're going to make some room here. In fact, what I'll do is I'll just draw up another blank document here. So we'll go ahead and rationalize, do one that's like a rationalization. So I'll do f of x is equal to, let's see here, I'll come up with one. We'll use x plus 2 minus the square root of 2 over x. So if I take this one, I can see obviously that x equals, well, let's see what we get. X equals 0 could be a problem because if I try f is equal to 0, I will get 0 plus 2 minus the square root of 2 over 0. And this will give me 0 over 0. Again, the indeterminate value. Sometimes we can use int to shorthand that. So that's not going to work for us. So obviously, well, when we're doing it, sorry, without a limit, should go backwards here. That is actually undefined because it is a function. So we're not doing a limit. So that's actually undefined. My bad. That is undefined. But when I do it as a limit, it's going to be indeterminate. So let's do it as a limit. X approaches 0. We'll use our function x plus 2 minus the square root of x all over x. Now we can put that in a bracket just to keep it handy. And we do that limit. That limit will be expressed a little differently, 0 over 0, which is that indeterminate bit. So we've got that. So what could we do with this? Well, we can do is we can rationalize it. So we can multiply this by a square root that would work. Now, in this case, the square root we'd have to use would be the the cojoint. So what we're going to do is we're going to take a value or a square root that's going to work for us. So if we have, in our case, x plus 2 and the square root of x, oops, minus the square root of x, what we need to do is we need to use the part of a square root. So we're going to use a particular form of this, and it's called the conjugate. The conjugate is actually the same rational, or radical, I should say, expression, but with a change in sign. When I do this, when I multiply by the conjugate, what I get is I use the square of the, right, multiply the first two in FOIL, so that is going to be x plus 2 radical, x plus 2 radical, which will be just x plus 2. So my first terms in FOIL actually remove the radical sign. The last two terms are going to be the square root of x, the square root of x with a minus sign. So that's going to also remove the radical. And the middle terms are going to cancel each other out. So this term is going to be root x plus 2, and the other term is going to be minus root x plus 2. So when I multiply the radicals, I'm just going to get x plus 2 minus x. And when I do that, I'm just going to get x, I'm going to get 2. So this piece here is going to reduce greatly to the value 2. So I can go ahead and do this as I'm multiplying this radical out. So when we start, we would have that limit as x approaches, lost it here, 0. So we'll start with our original expression. We had the square root of x plus 2 minus the square root of x all over x. Now I'm going to, we said was 0 over 0, so we're going to do this. Notice I have to rewrite the limit again. Now I'll write the square root of x plus 2 minus the square root of x all over x. And then that I'm going to multiply here by the square root of x plus 2 plus the square root of x. Now I can't just introduce a term like that without doing something to balance it out. So I'm going to actually make sure that I do top and bottom multiplication. That way I'm essentially multiplying this by 1. So here's my 1, my x squared plus square root of x over square root of x plus 2 over plus square root of x. So that part is balanced. Now on the top, we already did that work, but we'll do it again a little bit here. Square root of x plus 2, square root of x plus 2 is x plus 2. That takes care of the first two. The middle terms cancel, and the last term is going to be minus x. And the denominator, that's where I'm going to have that more complicated term. So that'll be x plus 2 plus the square root of x down here on the bottom. And the numerator, we already mentioned that that is going to be x minus x. So we're just going to have 2 in the numerator. And in the denominator, we're going to have x square root of x plus 2 plus the square root of x. And when I finish that off, now I'm going to do direct substitution again because I've simplified it down. So where I have 0, 2 will be in the numerator. If I look over here, let's see. That is actually going to be, oh, I was hoping for something better. Oh, well, it is what it is. It looks like we're going to get 0 here, and then the 2 root. Well, that's going to be messy. That's going to be 2 here. But this is still going to be 0. So it's going to be 2 divided by 0, which is going to be a problem that's going to be undefined. So the limit's not going to exist at that point. So we're going to have an issue, but that's fine. We determined that that is indeed going to be the limit. So try these examples out. You should be able to work with those, and we'll talk about this later.